All right, so let's finish up talking about the notes we started in class today. If you weren't there, I posted the blank notes online. If you were there, you should have the notes out in front of you so that you can take these down. So we talked about percentiles. So that's one way to measure location in a distribution. The other way to measure location is something called z-scores. So specifically, a z-score tells us how many standard deviations, I'm going to abbreviate, how many SDs from the mean an observation falls, and in what direction. So in general, how many standard deviations above the mean you are or below the mean you are. Depending on the situation, that may be a good thing or a bad thing, but that's what that measures. Okay, so the formula to calculate this. First we start with any individual in the observation, x. That's just any individual, anything in the observation. And then you know the observation or the distribution has a mean, x bar, and a standard deviation, s of x. And then we're going to get this standardized score. That's our z-score. So those are synonymous, standardized score and z-score. So here's how you calculate it. For a z-score, that's the individual. So how many standard deviations are you away from the mean? So let's start by subtract the mean and divide by the standard deviation. So symbolically, that's just z equals x, that's our individual, minus x bar over s of x. So that's our another measurement of location or distribution. We already did percentiles. Now this is z-scores, and this is a really popular thing throughout the rest of the course. So otherwise, a standardized score or z-score, those are synonymous. Back to our example about Ginny. So she scored an 86 on that test. I think we saw her to be in the 84th percentile. So for that class, the class average was 80, and the standard deviation was 6.07. So she got an 86. She's going to be our x. The class average, the x bar, was 80. The standard deviation, 6.07. So I'm just going to assign symbols to those. And I'm going to keep color coding things for this one too. So what's her z-score? First of all, it looks like she's above the mean, right? So it should be a positive z-score, right? And if she's an 86 and the standard deviation is 6.07, and I asked you how many standard deviations away she is, you'd probably say a little bit less than a whole standard deviation, right? She's 6 above the mean, and the standard deviation is only 6. But anyway, let's calculate it. So her z-score. Z is equal to her score, the individual, subtract the mean, divide by the standard deviation. So 6 divided by 6.07. So it's about 0.99 standard deviations above the mean. So almost one whole standard deviation above the mean for that distribution. Okay, so the basics about z-scores. How do you calculate and interpret it? Well, we've already calculated it. You've seen the formula. So how do you interpret it? Well, a z-score is how many standard deviations, SDs, above or below the mean you are. So that's another way to measure location and distribution, by guessing or judging how many standard deviations you are away from the mean. Okay, does it have units? Does it have units? No. So z-scores don't have units. It's a measurement of how many standard deviations, but you just say z equals a number. So they don't have units. Before we talked about like a standard deviation, those keep the same units as the distribution, but z-scores don't have units. You'll notice I didn't write any units on this 0.99 right here. So it's just z equals 0.99. There's no units on standard deviation. And last but not least, what does the sign tell you? So if it's a positive z-score or a negative z-score. Well, for a positive z-score, that really just means that you're above the mean. So Ginny being 0.99, she would be above the mean. And then obviously for a negative z-score, that means you're below the mean. To have a z-score of 0, I suppose that would mean that your value would have to be right at the mean. You'd have to have the same value as the mean to get a z-score of 0. All right, for example 6, it says Macy's a 3-year-old female. She's 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody's taller than Macy, but who's taller, relatively speaking? That is, relative to other kids of the same ages, who is taller? According to the Centers for Disease Control and Prevention, the heights of 3-year-old females have a mean of 94.5 centimeters. I'm going to underline that. So females is 94.5 centimeters, and a standard deviation of 4 centimeters. The mean height for 12-year-old males is 149 centimeters, standard deviation of 8 centimeters. So obviously her brother's taller than her, but relative to where they're at for their age group and their gender, who's taller? So if you go to the doctor's office, who's going to be in the greater percentile? That's one way we could measure it. Since we don't know exactly how it's distributed, how many they're above or below, let's calculate their z-score relative to the mean and standard deviation for the distribution and see who's taller. So let's start with Macy. So for Macy, and again, we're curious about who has a higher z-score. We're not going to do percentile because we don't know each individual distribution. There's probably millions of kids in that distribution. So who has a higher z-score? Let's start with Macy. So she's 100 centimeters. That's our observation for Macy. The mean for females, 94.5 centimeters, and the standard deviation for females is 4 centimeters. And notice I put a little subscript F on these, right? X bar for females, and then obviously for males I'll put X bar sub M. And then the standard deviation for females, instead of S sub X, when I'm talking about females, so a little more context, I'll just put S, the subscript F on there. Okay, so let's go ahead and calculate her z-score. So let's take her height, 100, subtract the mean, divide by the standard deviation. So for Macy, z-score 1.1375, which means she's about 1.4 standard deviations above the mean for girls her age. Okay, not bad. So let's look at her brother. Let's look at her brother Brody and see where he stands for males his age. So he's 158 centimeters tall. For that distribution, though, that he comes from, X bar sub M, it's 149 centimeters for the mean. The standard deviation is 8 centimeters. Okay, so his z-score, let's take his height. So z equals his height minus the mean divided by the standard deviation. So that's the pattern every time, right? Take the individual, subtract the mean of their distribution, and divide by the standard deviation of the distribution. That calculates how many standard deviations away they are from the mean. It looks like Brody's 1.125 standard deviations above the mean. So this should give you a clue. Who's taller for their group? For the girls in Macy's age group that are that age versus the boys that are in his group that age. For Brody, well, Macy's got the higher z-score, so she would be the winner in this case. Okay, so how do we say that in context? How do we conclude that in context? We know Macy's taller, so Macy is taller, but not taller than Brody in general, right? She's taller relative to females her age than Brody is relative to males his age, right? And that's what we were trying to solve. So for her age group of females, Macy's taller than Brody is compared to males his age. How do we base this evidence? So we concluded it, and how did we come up with that? Well, since she had a higher z-score. Should I say that? Since she had a higher z-score. Since she had a higher z-score. Okay, last example here. Example 6, Part A, Home Run Kings. The single-season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. These are the record setters here. So Maris hit 61 in 1961, McGuire hit 70 in 98, and Bonds hit 73 in 01. In an absolute sense, Barry Bonds had the best performance of these 4 players because he hit the most home runs in a single season. However, in a relative sense, this may not be true. Baseball historians suggest that hitting a home run has been easier in some eras than others. This is due to many factors, including quality of batters, quality of pitchers, hardness of the baseball, dimensions of ballparks, and possible use of performance-enhancing drugs. No, none of those guys use that. Come on. To make a fair comparison, we should see how these performances rate relative to others hitting during the same year. Calculate the standardized scores for each player and compare. Okay, so aside from all the steroids and harder baseballs and maybe they had more games in Barry Bonds' year for Babe Ruth year, who is the best for that era? So that's what Z-scores allow you to do. You can compare relative to their distribution who was the best. So let's look at each one of these players. Let's start with Babe Ruth here. So I'm going to abbreviate BR. He's going to be in black here. So he hit 60 home runs. So for his Z-score, 60 minus his mean was 7.2. Divide by the standard deviation for him, so 9.7. So for him, he's looking at a Z-score of 5.44, which is actually really impressive. So he's 5.44 standard deviations above the mean. I'm going to add him to the list here, 5.44. Okay, well, the next record breaker here, Roger Maris. Let's calculate his Z-score for that area. He hit 61 and 61, apparently. So RM. So he hit 61 home runs. The mean that year, it went up. It was 18.8. Divide by the standard deviation of 13.4. So he is at 3.15. So not really close to Babe Ruth right now, which should make somewhat of sense to you. Like, Babe Ruth hit 60 home runs back when the mean was only 7.2 home runs a year. That's a big difference, right? To be 5.44 standard deviations above the mean, that's a big difference. Whereas Maris when Maris broke and hit 61, people were hitting 18.8 on average. So that's a lot bigger mean to compare to. Okay, well now let's look at McGuire. Magical season of 98 when Sosa and Griffey and McGuire were chasing home runs, right? So he had 70 that year. The mean was a little bit bigger than 61. It was 20.7. To divide by the standard deviation, 12.7. He's at 3.88. So better than Maris, but not nearly as good as Babe Ruth, apparently. And lastly, who do we got? Big Barry Bonds. Big Barry Bonds. He was clean. He was clean. I don't believe in anything that the court says or anybody else, Balco. So for his Z-score, subtract the mean, divide by standard deviation. 3.91 is his Z-score. So just based on this information right here, these three players, Maris, McGuire, Bonds, they're all pretty close, but none of them even come close comparing to Babe Ruth, right? 5.44. So he was just way above and beyond in terms of dominating his era for home runs. So we answer this in context. Babe Ruth dominated his era. He dominated his era the most. Having a standardized score, or you could say Z-score, having a standardized score, it's 5.44, which is well above the others. So that's our evidence in this case. Babe Ruth had a standardized score well above the others. And just to give you an idea, here's a picture of Babe Ruth, the king. He was the king then. He's a king now in terms of dominating his era. So, great for him. Okay, last little bit here. It says in 01, the Diamondbacks' Mark Grace's home run total had a standardized score of Z equals negative 0.48. Interpret this value and calculate the number of home runs he hit. Okay, so we don't know how many home runs he hit. All we know is his standardized score, Z equals negative 0.48. So in general, he's below the mean, right? In general, he's below the mean. So to be exact, when we interpret this, we can say that Mark Grace was actually 0.48 standard deviations below the mean. Below the mean what? The mean home runs for 2001, okay? So that's part of our context. If we just forgot this home runs piece, he was below the mean, you would lose points on the AP exam, right? Context of the question means you need to leave that in there. This is home runs for 2001. The mean what? The mean has units, okay? So he's below the mean home runs for 2001. How do we find out? How do we calculate the number of home runs that he hit? So how do we calculate the number of home runs that he hit? Well, you have a formula for Z-scores, right? And in fact, so if you know his Z-score is negative 0.48, and you know it happened in 2001, if you look at the table, we have the mean for 2001 and the standard deviation. So we've got 3 of those pieces that go into that formula. So let's look there. So 2001, we know the mean. That's in the table. We had it for 21.4. Same year Barry Bonds was up. The standard deviation that year was 13.2. And so his z-score, Mark Grace's z-score, was negative 0.48. So right now we've got 3 of the 4 values that we need right here. These are 3 of the 4. The only thing we're missing is the actual number of home runs Mark Grace hit, his individual observation. Okay? So let's look at the formula. We know it's x minus x bar over the standard deviation. And of these values, we have a lot of these taken care of, right? We have the z, we have the x bar, we have the standard deviation. The only one we don't have is the x. The only one we don't have is his individual observation. So let's go ahead and just substitute those values in there, and we can come up with the number of home runs that he hit. So we're going to actually solve this for x. Let's substitute. The z was negative 0.48. The x bar was 21.4. The standard deviation of x was 13.2. Well, if you look at that, the algebra is not so bad, right? And I've talked about this before, but the algebra and AP stats in general is really not that heavy. So now that we've got the setup, the z-score formula, now we're just really going backwards to get that x, that individual observation. So to get to it, let's start by multiplying both sides by 13.2. So that cancels out on the right-hand side there. 13.2 times negative 0.48, that's about 6.4. Negative 6.4, I should say. So last step, just add 21.4 to both sides. What are we talking for old Mark Grace and his home runs? Former Cub, by the way, for a number of years. 15 home runs there for Mr. Grace. All right, that's it for this video. See you in class.